The topic of this episode of Quantum on the Back of an Envelope is quantum fractals. More specifically, we'll look at a very simple quantum mechanical system, a one-dimensional particle in a box, in which the particle's wave function takes on a fractal form. But first, what exactly is a fractal curve? In general, the graph of a function may look intricate, but intricacy alone does not make something fractal. For example, the function y equals sine of x squared shows increasingly rapid oscillations, with the oscillation frequency growing without bound as x gets larger and larger. If you zoom into this function, however, those apparent complexities smooth out. At a certain magnification, the curve looks locally like a straight line. In other words, the function is smooth, not fractal. Fractals are different. For certain functions, zooming in never eliminates complexity. No matter how deeply you magnify the graph, new details continue to emerge. These are fractal functions, and their defining feature is structure on every scale. So, can the wave function of a quantum particle, or equivalently its probability density, be fractal? The short answer is yes, but with a catch. Let's look at one of the simplest known examples, first studied by Michael Berry. The reference to his original paper can be found in the description to this video. Consider a quantum particle trapped between two hard walls, the classic particle-in-a-box problem. To simplify the math, we'll use atomic units, where the Planck constant and the particle's mass are both set to 1. This system has infinitely many bound states, each with its own energy level, E1, E2, and so on. The nth energy level corresponds to a stationary wave function of a standard form. Any time-dependent wave function describing the particle's motion inside the box can be written as a superposition of these bound states. Here, t represents time, and the coefficients of the expansion, the Cn values, determine the particular superposition. These coefficients must satisfy a normalization condition. Up to this point, everything we've said is standard textbook quantum mechanics. But here's where fractality comes in. If we choose the expansion coefficients in a very specific way, equivalent to starting with an initial wave function that is simply constant everywhere inside the box, and then look at the system at a very particular time, namely when t is given by the golden ratio, the squared modulus of the wave function develops an extremely jagged structure. Careful mathematical analysis confirms that this function has structure on every scale. In other words, it is a fractal. And because the squared modulus of the wave function represents the probability density of finding the particle inside the box, the probability distribution itself becomes fractal too. We won't go into the mathematical details here. That would take much more than the back of an envelope. But the essential point is clear. Quantum mechanics can produce fractal wave functions. Finally, can such a fractal state actually exist in the real world? Probably not. The reason is that the exact wave function we just described corresponds to a particle with infinite energy. In principle, by giving the particle more and more energy, its wave function could approximate the fractal state more and more closely. But the exact fractal state itself cannot be realized physically. We hope you enjoyed this episode of Quantum on the Back of an Envelope. To learn more about what we do, please visit us at our website.